Well, the question will also be how do you approach development of the particular operator, and the operator lifecycle model or maturity model helps to segment your development into various stages. Personally, I'm not really sure whether I would approach an operator in that particular manner. For example, I think that backup and restore is such a fundamental ability. I'd rather have a single replica Postgres with a backup and restore than to have let's say a minor version upgrade already, because in my opinion, the first moment I spin up a database, I want to be able to create a backup from it, whereas I can wait some time until I upgrade it. However, this is, as I said, context specific. People have different views on that, and any attempt to bring use cases of the entire set of lifecycle, use cases of a data service into a particular sequence as a general guidance will always fail in particular contexts, because it's so context specific. People have to apply their own priorities. So as we assume to use Go, we'll be able to cover all the entire 5 different levels here postulated in that model. As I said, it's more or less a rule of thumb, kind of advice on how to, ask yourself whether you've created an operator with the most essential features. There's many more you have to look into, and there's common pitfalls in writing operators, including underestimating the entire complexity of writing an operator, or not covering essential lifecycle operations, having only limited robustness, and being not very predictable, for example, in the event of simple failures. And of course, if you take an operator, for example, created for a different context, let's say a small organization, and you apply it to a large organization, they will see, well, there's a lot of missing compliance with, for example, their security handbooks. In this regard, it's always interesting to see what do people actually want. So what does the average organization want? Now, the list I'm presenting here is compiled from interviewing large organizations. They often have thousands of employees, and you will see that if you have a small startup, let's say, your priorities could deviate. So exposing the lifecycle using custom resources is idiomatic in Kubernetes, and I think that's a common sense kind of a statement. The idea of on-demand provisioning dedicated service instance has also become very popular. So a service instance should be represented by a dedicated Postgres cluster. For example, having a single pod in a stateful set, or having a pod with several replicas in a stateful set as your service instance. That is on-demand dedicated. Whereas a shared Postgres would, for example, be a static a stateful set where your service instance will be, shared access to that particular Postgres. Like in our approach here, we believe that the operator should be able to create many Postgres instances, not only one, and then use the concept of service bindings to provide ability to connect applications and create database uses, for example. So we'll cover that later. So you want to be able to set certain configuration values, for example, Postgres variables and so on. Basic monitoring of the service instance health is necessary. For example, if it's clustered, what's your replication like doing? You want to avoid a runaway replication like where you could have and run into data loss situations. You don't want to tie into infrastructure too much. For example, when creating backups, you have to store the backup somewhere, and streaming a backup to an object store will require you to make assumptions about its interface, and being agnostic here, or at least providing an adapter pattern to be extensible, is something that you should take care of if you want to serve the operator, or if you want to deliver the operator to a broader audience. For the same reasons, offering compatibility with various Kubernetes flavors is essential. And when providing access to databases, you also need to maintain best practices of securing access to a database. For example, if you have two applications accessing the same database, they should have separate sets of access credentials. And as we've seen with the service binding concept, that can be achieved pretty easily. Scalability of service instances in both horizontal and vertical scale is necessary and meaningful, which means that if you start with a single pod stateful set, you want to be able to turn it into a three replica stateful set with asynchronous streaming replication, for example, and maybe even 5, 7, 9, the 2n+1 scalability to enable quorums. If you have multiple nodes in a Kubernetes in a Kubernetes-based service instance, such as a Postgres asynchronous streaming cluster, you also want to have automatic failure detection, which is not a built-in feature into Postgres. So you want to go with Rep Manager or more preferably maybe Patroni to detect and respond to failures of, let's say, individual pods. Once you've done that, you also want to ensure if the pod comes back, it won't, create you a multi-master situation, for example. So the reintegration or the recovery from degraded service instance is also something that you want to provide. When clustering service instances and having stateful sets, they should be aware, of the underlying Kubernetes node. So you should have a distribution of pods across several Kubernetes nodes and ideally across several availability zones in the infrastructure. So that if, for example, power, the cooling, fails in the data center, we're taking down maybe an entire availability zone or network switch fails so that, the other availability zones remain unavailable and therefore your service instance remains available if pods are spread in a Kubernetes cluster that spreads availability zones. You want to turn small databases into large databases. Obviously, that's something that will be necessary from time to time. If databases grow, they will have more resource consumption. Providing backup and restore capabilities with the ability to create backup schedules is something that seems essential. If you run a database in a production environment, you want to be sure that if really problems emerge, you'll be able to recover from a database. Whether this is to protect from failures of the infrastructure, the platform, or let's say human failure of application developers or platform operators, doesn't matter. A backup is often a good fallback strategy to avoid large disasters. Streaming backups to external storage helps to be more to help to replicate to offsite regions, for example, so that if the entire data center goes south, you'll be able to recover a service instance in a different region, for example. Application developers want different data service versions. Some are more progressive, they want the newest versions. Some are less progressive, more conservative. They will wait before individual upgrades. So giving them the granularity of control they need for their work is essential for the acceptance of automation in an organization. Well, documentation, obviously, and encrypting data sitting on disks, as well as being transferred from clients to data service instances, but as well as the nodes of the data service instances in, for example, interpod communication in a stateful set. Data service instances are usually long-lived in a way that, a database lives as long as, for example, the corresponding applications live, which could be many years. So you need to understand that throughout the years of such a database's life cycle, there will be many events and the automation will have to guide the application developer and the data services and the data through all these different events. Here's an incomplete list of things that will happen to data service instances over time Well, installing the operator is one category, and managing the operator lifecycle. Creating the service instance, connecting an application, adding a log sync, scaling it up, scaling it out, applying some version upgrades, attaching applications, which is the creation of the service binding, creating backups, restoring them. But also, it is very likely that throughout these years of existence, they will also see failure scenarios. For example, that could be a fluctuation in network delay or bandwidth, or that there could be a network partitioning, or that there could be failing hardware nodes. Let's say a Kubernetes node goes down, or an entire availability zone. So all these events, they are likely to happen throughout the years, and therefore represent events that should be considered rather ordinary than exceptional. We've talked about service bindings quite a few times, but what is a service binding? Because it's not common terminology in the Kubernetes ecosystem. The term has been borrowed from the Open Service Broker API specification, which emerged in the Cloud Foundry ecosystem, and basically represents an abstraction that allows applications to connect to a data service instance in a secure way. It is doing that by, for example, creating a secret and a Postgres user. So if your application wants to connect to a database, it has to know what is the host, what is the username, what's the password, and maybe some other parameters that are required to do the connection to the database. And while you can store them in Kubernetes secret and reference the Kubernetes secret in your application deployment specification, you also need to create a corresponding database user and ensure that these access credentials actually do something, and that there's authentication for an existing user in the data service instance. And that's a procedure that has some technical complexity. Idiomatic in Kubernetes, in our beliefs, is that this should be represented as a custom resource rather than something some options that you hide under the object specification of the data service instance itself. The service binding has its own life cycle. For example, if you add an application, you want to create a service binding, and if, for example, the application has been compromised or it has been removed, you want to also be able to remove the service binding along with the Postgres user to ensure there will be no data leakage in this context. So this is also a good example that we'll revisit later because we have to reconcile external resources, how to create a data service user. Here, a Postgres user, for example, is an interesting challenge in writing operators. Backups is another essential feature of an operator, and in our opinion, backups should be represented with CRDs. There should be a backup plan, and backup CRDs can be perceived similar to a cron job and a job. So a backup is something that will take some time to create, time to execute successfully, and you want to do that on a regular basis. So you want to be able to describe a temporal pattern, let's say a schedule, when backups should be created.